Hello there. Welcome to the last lecture of week 10. This week we've been looking at object-oriented applications, testing of object-oriented applications. We saw several different issues, features of object-oriented applications. All the issues basically concentrate on one part, which is on the call interfaces in the presence of inheritance, dynamic type binding, and polymorphism. It's difficult to know which methods of which versions of the polymorphic methods will run, and that can cause a whole set of issues. Yo-yo graphs were call graph representations for call interfaces for object-oriented programming. We also saw cataloging of faults. In this last lecture, we'll go back to test requirements for call graph coverage criteria and look at test requirements in the presence of all these object-oriented features, dynamic type binding, polymorphism, and in the absence. So we look at coupling variables, define coverage criteria based on coupling variables for call interfaces with object-oriented features and without object-oriented features. So here is a recap. Remember, we are doing one method calling another method. The two methods typically reside in different classes, maybe an ancestor and a descendant class, parent and a child class. And based on the inheritance and the polymorphism that is present, it's difficult to statically determine which version of the method is going to be called. So without these call interfaces, when we did graph-based testing, we had looked at design integration testing. And at that time, we had defined all these notions that you see here in this slide. A coupling variable is a variable that is defined in one unit, used in the other. Then we couple, instead of coupling definitions with uses, we couple the last definitions with the first of the uses. Last definitions basically are the definitions that occur just before the call, at the call site, just before the call site happens. So last definition is the set of nodes that define, let's say, a variable x, and further there is a definition clear path for x from that node that defined the variable x, and this path goes through a call site to a use in the other module. So this can be from the caller to the callee or callee back to the caller as a return value. First use is basically all those nodes that have use of the coupled variable y and for which there is a definition clear and use clear path from the call site to the nodes that use it first. A coupling du path is a definition use path from the last definition to a first use. The same example we had seen earlier when we looked at graph-based testing. So here we have two procedures, F and G. F is the caller, G is the callee. F has some code, and we don't really worry about the full code, but focus on the call interfaces. Let's say at some point, the procedure F is calling the procedure G at this statement, y is equal to g of x. So that becomes the call site, and x is the variable that is used in the call as a parameter. So look at the last place before this where the variable x was defined. So this is the statement where x was defined. X was 14. All these statements in between don't redefine x. So the last definition of x is passed through the call site, the statement at which the call is made, y is equal to g of x, to the first use in the callee method g, where it is coupled with a and print statement is its first use. Similarly, now the code for g runs, and g returns a value b back to f, and b is coupled with y. So the last definition of b occurred here, b is equal to 42. In between, assume that there weren't any further definitions of b, and the return value b is coupled with y and printed out, and this is the first use for the last definition that was here. So this is straightforward. Methods f and g are not polymorphic, they are not owned by different classes. This is just ordinary call graphs. This is fine. Coupling sequences in general can be defined in several contexts, with or without object-oriented features. So they represent a pair of method calls for object-oriented programming. Let's say there is a method, let's call it f, and that is being tested. Inside that method, some more methods are being called. Consider a pair of method calls within the body of this method under test. This should be made through a common instance context as far as dynamic binding is concerned. And this is made with reference to the set of variables that are referenced, that is defined and used by both the methods. And it will consist of at least one coupling path between the two method calls with respect to a particular state variable. So these coupling sequences represent potential state space interactions between the called method with respect to the calling method. And they are used to identify the points for integration, that is the call interfaces, which we further use for testing. So we'll see some definitions and illustrate those definitions through some examples before we actually define the test requirements as criteria. So in this definitions below, assume that small o, lowercase o, is an identifier whose type is a reference to an instance of an object pointing to some memory location that contains an instance which is a value of some type. Let's say that is a value v. So this o, object o, reference o, can refer to instances whose actual instantiated type could be of two different kinds. They could be the base type of o, or they could be a descendant of O's type. For example, in the programming language Java, if you write a statement like this, O is equal to new of B, then for this object O, O's base or declared type is that of A, and its instantiated type or actual type at runtime is that of B. So object O is considered to be defined when at least one of its state variables is assigned a value by in the object O. So polymorphic call set, this we've already defined, but remember, in the presence of polymorphic methods, it's difficult to determine which would be the actual method that will run. So if a particular object is defined by any one of the methods, it could be indirect definition because it could be the actual type, base type, or it could be the base type, or it could be the original base or the declared type, or it could be the instantiated or the actual type. So you collect together all those methods and put them as polymorphic set, also sometimes referred to as satisfying set. So definitions and uses in object-oriented applications for coupling variables can be indirect. We don't know which method will refer to it, will define it, will use it. So we say indirect definitions and uses occur when one method, some method, defines or uses or references a particular value v. In the presence of indirect definitions and uses, with the scope of more than one method defining it at different executions, we typically consider all the methods that can potentially execute. We put together all the methods and call it the polymorphic call set or the satisfying set. Satisfying set is the set of methods that can potentially execute as a result of a method call through a particular instance context. So here is a control flow graph. The text is small, but I hope you're comfortable reading it. This topmost part where my mouse is pointing to is the method f. So we call it the coupling method. The definitions are there in the next slide. So this method starts at this white oval colored edge. That's the beginning of the method. Some code runs at some point, and this node, black circular node labeled I, it defines an object O. And then later down at this node, it does a function call, method call, where it calls this method M. The method M that is being called, we refer to it as the antecedent method. Then control enters this method M, and this definition is passed on here at this node J, and then some code runs, and this O is assigned this value V and passed down here, and then the control returns back to the parent method F, and we call this path that returns the control back, the call interface path, as the transmission path. It's the same as call interfaces. And then here the set of values that are assigned are object O, and O, inside O, V is specifically assigned, O, O dot V. And then the next call happens to another method N, that's called the consequent method. Why is it called the consequent method? Because whatever the antecedent method M defined, the consequent method is going to use that value. So the definition occurs in the antecedent method. The use occurs in the consequent method, and the consequent method passes the control back to f. So there is this the initiating method, the starting method, which we call the coupling method f, that goes through some code, defines a particular object, and at some point calls a method. That particular method uses an instance of that object. Redefines an instance of that object, then control passes back to the coupling method. Then the later point in time, coupling method calls a second method called consequent method, which ends up using the one that was defined in the antecedent method. After using, the control passes back to the coupling method. So this exhibits a typical way in which control is passed back and forth in the process of objects being defined with their actual types. So this is a recap of what a coupling sequence is in the context of object-oriented programming. This is a pair of nodes that call two methods in sequence. Here, for example, it first calls method m, then calls method n. First method defines a variable, the second one uses it. That's exactly what we saw here. It defines o.v here, n uses o.v here. Calling method is called the coupling method, which is this method f on the leftmost side. It calls m, which is called the antecedent method, that defines the variable, a particular variable under consideration, followed by the consequent method n, which uses that variable. Transmission set is the def clear paths, what we earlier called du paths, but they were void of any definitions in between. Here they are referred to as the transmission set. So in this figure, if I start from h here on top, then go to I, go to j, come back through k, then go through L, and then come back, then that constitutes what we call a transmission path for O.v. And the object O is the context variable. Is this clear? More or less the same thing. We are talking about call interfaces, but we are talking about one coupling method calling an antecedent method which defines a value. Control goes back to the coupling method, and later it calls a consequent method which uses that value. It could be the case that f is the same as m, the antecedent method, or it could be the case that f is the same as n, the consequent method, in which case it is very similar to what we saw as the call interfaces earlier. But here, this kind of behavior could also happen. So we call such a sequence as coupling sequence, the sequence from S, J here back to K. One caller method, antecedent method, control back at the next call site to the consequent method. That's called as SJK. Then one more definition, theta SJK superscript T is the coupling set of this coupling sequence SJK. It basically represents the intersection of the variables defined by M, used by N, through the instance context provided by a content variable O that is bound to an instance of T. Is this clear? Basically, take all the variables that forms the coupling set. As usual, the M and N can be polymorphic and different versions of it could run. So it is determined by the actual type T of the instance bound to O. Basically, in summary, we use the same kind of call interfaces. We give slightly different names and try to separate F from M and N. And we do this separation because we want to be clear about there could be different variants of the method M that run. M could be polymorphic. There could be different variants of the method N that runs. N could be polymorphic. M could be merged with N. F, N could also be merged with F. So it's very similar set of definitions as we saw earlier for call interfaces, but slightly different terminologies because we would want to include the satisfying set or the polymorphic set. So here is an example of coupling sequence. On this left, the picture that you see is a class inheritance hierarchy. There is a parent class W, child classes X and Z, which in turn has another child class Y. Y is the descendant of W. Let's say we have an object O that is bound to an instance of W. The rest of the part is read similarly. W has two variables V and U, three methods M, N, and K. X has one variable X, a method N, and so on. Now you do the same thing. That is, you consider such a picture here, but replicate it for this class inheritance hierarchy. Suppose an object O is bound to an instance of W. Then in the coupling method F, I define, then I call, then W's version of M runs, which ends up defining the variable V, goes back, comes down, which W's version of everything gets defined, because object O is bound to an instance of W. That's what this picture says. Whose version of a variable gets defined by which corresponding method. Here O is bound to an instance of W, so W's method runs to define W's variables. Suppose you take the same class inheritance hierarchy that is on the left, but now instead an object O is bound to an instance of Z, right? So for the variables that are local to Z, like X, and the corresponding methods M and N, the versions that run in the last picture here, the versions that get used up and partly defined are those of Z. So X, which also corresponds to Z, the W's version of M runs to define X, and W's version of U gets defined because U does not belong to Z anymore. In terms of uses, Z's X gets used, the one that gets defined by Z's M. So a picture like this can be visualized in the context of a class inheritance hierarchy like this, and which versions of which methods execute for defining and using the various variables depends on where the object O is bound to an instance of which class. That's all is being said. Now let's define testing criteria for object-oriented coupling. We want to test how a method can interact with an instance bound to an object O. Interactions can occur obviously through coupling sequences. We consider the set of all interactions. What are the various types that can be bound to O? Which are the methods that can actually execute? Consider the entire polymorphic call set and test for all possible options with all possible bindings that are possible. So that gives rise to 4 criteria. Let me just move on and show you these 4 criteria. So one is all coupling sequences, the one that you see down below here. The one right at the top is all poly coupling definitions and uses. To the left is all poly classes. To the right is all coupling defs and uses. So if you see, there are 2 things that use the word poly. So they consider poly short form for polymorphism. They consider polymorphism, so which means they consider inheritance and dynamic binding. 2 of them don't consider. So they don't have that short form polymorphism, poly for polymorphism. So that's the 4 criteria that we're going to define. The first one is all coupling sequences. Look at the second and the third bullet to start with. It says at least one coupling path must be executed. Don't worry about inheritance. Don't worry about polymorphism. So this is the same as saying, look at the last definition and go to the first use. At least one test case. This is the good old thing without any kind of polymorphism, inheritance, or dynamic binding. It's defined in terms of the new definitions that we saw. Coupling methods, these definitions here, and the coupling sequences. But it's the same as the good old call interfaces, no difference. Next is all poly classes. Here, it includes, if you look at the last 3 bullets, it includes the instance context of the calls. At least one test for every type the object can bind to is tested, and it tests with every possible different type substitution that can occur. For every coupling sequence SJK in the coupling method F, for every class in the family of types defined by the context of SJK through an inheritance hierarchy like we saw in that example, there's at least one test case T such that when this method is executed using that test case T, while the test case T is running on that method, I should be able to find a path P in the set of all coupling paths of SJK that is a subpath of the execution trace of F on T. So this includes basically at least one test for every type the object can bind itself to. So it says for every class in the family of types. The next one is all coupling definitions and uses. This is different from this one. This says all coupling paths from the definition. Here all coupling paths from the definition to the uses without polymorphism, without inheritance. This is just the same thing as the earlier criteria. plain graph coverage criteria, but this is for DU paths. First definitions to last definitions to first use. No inheritance, no polymorphism. Now I can add inheritance and polymorphism, consider last definition to first use, and consider every kind of type binding. Then I get all polycoupling defs and uses. So if you look at the last few bullets here, every last definition of a coupling variable reaches every first use for every kind of type binding across the class inheritance hierarchy. This is the mother of all the previous criteria. It handles inheritance, class inheritance, it handles polymorphism, it handles dynamic binding, takes both definitions and uses of each of the coupling variables into account. So this is the most expressive of all the coverage criteria. The first part here is the formal definition of it. What does it say? It says take a coupling sequence SJK in the coupling method F. For every class in the family of types defined by the context of SJK, through an inheritance hierarchy like we saw in that example, for every coupling variable V of SJK, for every node M that has a last definition of V and every node N that has a first use of V, there's at least one test case T such that when this F is executed on that T, there is a path that goes through this coupling path of SJK. This will consider it for every class in the family of types. Is that clear? So these are the 4 coverage criteria that we saw. Obviously, the most expressive is all polycoupling defs and uses because it takes you from every last definition to every first use. Based on the class inheritance hierarchy, considers all possible type bindings that are possible. The ones down below and the one on the right are the good old call interface coverage criteria. The one on the left is all definitions in the presence of polymorphic calls. So we presented, just to summarize what we did throughout this week, in terms of object-oriented applications testing, we saw a graph model for understanding, visualizing faults that occur as a result of inheritance and polymorphism. We saw yo-yo graphs. We saw definitions and uses of state variables, polymorphic call sets. We listed a catalog of faults, a model for faults, and we also defined specific test criteria for detecting these faults. So with this, we'll come to an end of object-oriented testing. This one small bit about metrics, quality metrics for object-oriented software, which we will deal with in the last 2 weeks that we have. I'll stop here for now. Thank you.